All right. Good afternoon, everybody. So we're going to start here, and I'll kindly ask if somebody could maybe just confirm if you can hear me just fine, and wonderful. I had an experience. Two things, right? First, anyway, I think I'm probably going to talk about some of these things later on, towards the end. I think there were a lot of wonderful, kind of presentations that were made by people at the conference that I was attending, ICICT conference. There were people doing all sorts of amazing things as they relate to what we're discussing here. Garbage collection, traffic monitoring, as it relates to, I guess, the city of Lusaka, for instance. Dr. Halubanza was giving a presentation on again linked to traffic, but kind of system that is aimed at trying to make sure that there's a bit of sanity here when you have a lot of vehicles on four-way stops. Usually, if you figured out, you notice that the traffic lights are designed in such a way that they only activate, right? So they turn green, amber, and all that, and red after a predefined period of time or something like that. And so you're showcasing how him and his students were building a system that is meant to be slightly more intelligent. So a couple of interesting things. And I think what I will do is I will share some of these papers, I guess, or try and see if I can collect the presentations that were made, so that you can have a sense of what is possible out there. What is possible out there. There was somebody who was presenting models that they implemented to predict yield, crop yield ideally, which I thought was interesting, using geospatial images. But what you begin to notice is that all of these things are essentially the same. But something else I wanted to share was yesterday, as I was rushing to, I had an engagement at Zigta, and I was stopped, right? Somewhere I was passing through.
This is our test. Sit down.
Mr. Moses, do you want to mute your microphone? Thank you. I was passing through Kudu Road, and the police mounted some checkpoint or something. They normally do these random things here. So they stopped me, and it's like, you were supposed to be stopping there and stuff. Now I'm always rude like that when these people try to be funny and stuff. But what caught my attention is the fact that they still use a manual process. One of the things I asked them to do is to give me a charge sheet. Very strange lot, by the way. Give me a charge sheet. Now, what I do when I get documents myself is I scan them, right there and then, because I tend to lose documents. I don't want to lose documents. And this cop says, "Why are you capturing? You shouldn't be capturing." I'm looking at this person and are you insane or something? You're giving me this document. I'm going to go with it at home. It doesn't matter whether I capture it right here or when I'm at home. I'm still going to capture it. I think the impression they got was that I was probably going to share it on social media. Usually, you tend to behave like that when you know that the things that you're doing don't make any sense, right? I think what the average person does when they bump into those characters, I don't want to call them characters because that's what they are, right? Insane. What the average person does is they'll try and avoid the hefty fines, even when they're lying, is it? But I am adamant, right? Give me a charge sheet and I will go and pay. In fact, I will argue this, But anyway, so I sat down, I'm looking at this traffic offense report, right? I'm looking at it literally right now. It's manual, and the police have no way of tracking. I'm pretty certain there's a lot of interesting, AI-centric, kind of problems that can help address this issue, or solutions that can help address this issue. A lot of interesting problems. I imagine there's issues to do with OCR, nothing to do with machine learning here, but maybe a little bit of natural language processing, right? Because you'd want to extract information from the report and analyze it somehow, in Sen. Anyhow, we're going to continue our discussion. When we met last time, we had an appreciation of what evaluation was all about. We gave you an idea of the broad spectrum of evaluation techniques. And towards the end, I emphasize this notion that experimentation is crucial, right, to implementation of machine learning applications, machine learning models, or indeed AI models or applications, right? So the ability to measure the relative success of what you would have implemented. Yeah. And we I think we parted ways when I was explaining this workflow. The fact that, when you're experimenting with machine learning models, you typically go through the same process you go through when you're conducting any sort of experiment, right? You have got to, properly plan for the experiment. So you define your experimental settings. If there's need for you to design experimental tasks, you design your experimental tasks. You prepare a data set, and then you outline explicitly experimental procedure indicating the range of experimental factors that you'd be working with. Now today, I thought would transition to our discussion of part 3 here, which is supervised learning. And just to put it out there from the outset here that, supervised machine learning, is a standard process for building and evaluating predictive models, ideally. And the typical workflow of supervised learning starts from data, right? Using this data that you'd have gathered, right, as part of data preparation, what you would do is you would split it, right? In fact, the very first phase is using your data. You split the data, okay? And the reason you split the data is because typically when you're training these predictive models, supervised machine learning models, is you train them in such a way that, or rather you implement them in such a way that you, first of all, learn the models, or you train the models. And then after you train the models, you have got to test the models. And so what that means is that you'd have to split your data at a bare minimum into 2 separate groups, the training data set and the test data set. So you learn your model, you split the data, you train the model, and then you evaluate the data. So when you split the data, the training uses the training data set, the evaluation on the model uses the test data set. In between training and evaluation, you may find yourself tweaking the model, if you will, right? Optimizing it. So changing or tuning the so-called hyperparameters, depending on what sort of estimators you're using. And so what you tend to do in that particular case is you have 3 separate sets of data. So you'd have a validation data set, which you use to play around with these hyperparameters here. And then you deploy, right? Now, the deploy component here is in parentheses because we're not really going to focus on this. We were taught how to program a long time ago. I think 3, if not 4 years ago it was. So you know how to do this. Now, what we're saying here in terms of the steps is that step 1 is you start with the data. Again, it's important to stress that with supervised machine learning, this data is just not any type of data. It has got to be a labeled data set. And the labeled data set comprises of 2 types of data, right? Your input features, your X's, and your target, right? Which is your Y. The 2 are what collectively will comprise what we're calling a labeled observation in this particular case. And then multiple observations will comprise your labeled data set. Again, I want to draw attention to our equation Y is equal to f of X, where we said that those X's could be a whole range of input features, if you remember. Yeah. Anyhow, another way of thinking about this is the fact that your f of X, your Y is equal to f of X represents what in research, I'll have to share this as part of the notebook. I was trying to see if I could run code here. But another way of thinking about this is that when you have your equation Y is equal to f of X, yeah, it's like your X's, These are your independent variables, right? And your y is your dependent variable, right? The thing that you are, these things will be, can potentially be altered here to get a desired effect, which is y, and then the y is what you're measuring. That's another way of thinking about your y is equal to f of x. Anyhow, and then part two, we're saying is we split the data. We're dividing the data into separate data sets. These are like subsets of the initial data set, the labeled data set. And you're separating the training from testing. If you remember when I was outlining the key concepts associated with machine learning, there was this example analogy I was giving about you being assessed, right? As part of training you for the exam, what we may do is we may ask Dr. Mkelebai to give us questions, right? Sample exam questions and model solutions from last year and from previous years, in essence. So you would go through those problem sets so that when the time comes for you to write the exam, you would obviously get significantly more scores than you would get if you didn't go through past exam questions or something like that. So you would be training you on past exam questions, right? Now, the idea behind splitting data here is it would not make sense for us to reuse some of the questions from past exam questions and ask you those questions in the exam that's coming away in October, somewhere there. You understand? So we separate the two. And then part three is you learn the model, you train the model, right? And so what typically happens here is the algorithm learns, or the algorithm or estimator learns patterns from the training data. This is why, giving it a series of examples works in your favor, right? Because you need a lot of examples to show it different sort of patterns and corresponding or associated targets, right? If you see a combination of these features, this is the target. If you see a combination of these features, this is the target. Collectively, it turns out that it learns in such a way that it becomes so good enough that it will be able to tell you something that is closer to the truth, if not the truth at all. And then you evaluate the model. So the model that you would have learned in step number 3 is evaluated to assess its relative performance. Now, I want to stress here that the evaluation we are mostly focusing on, insofar as supervised machine learning is concerned here, is effectiveness. Okay? So we are measuring the trained model's performance. In other words, we will be looking at things like the accuracy, for instance, for both regression models and classification models, right? Classifiers. Or we'll be looking at things like precision and recall, or F1 score, right? If you remember that, the harmonic mean of precision and recall. Anyhow, and then number 5, right, which is something we're not really going to cover here, is if you are happy, right, or if your client or customer is happy with what you would have implemented, the model that you'd have implemented, you can then deploy this. Now, deployment could be in the form of, you building a series of RESTful APIs here, or perhaps web services that can then be integrated into much larger application. We can build a dedicated application for users to interact with the model, right? Anyways, for users to run inference, in other words. Now, a few terminologies here, right? Now that we understand the process itself, it's a simple process, right? If you notice, 5-step process in essence. It turns out that it becomes important for us to understand some key terminologies. Some of these things we've already discussed, but I'm going to put it out there so that we are all on the same page. Whenever there's mention of the word features or feature, we're going to represent this in code with uppercase X. And the reason it's uppercase X is because it's a set, is it? A set that comprises multiple features, right? So the features are the input variables which you use for prediction. In our example dataset, or the student at risk of failing dataset, some example input variables or features that would help us predict the examination outcome, which is our target, are course workload, course engagement, which is represented by, the hits on Moodle, the number of times that a student will access Moodle, or their accommodation status, whether a student is accommodated on campus or not. Now, already had a discussion about this data set here. Course workload is numeric. Moodle hits the numeric attribute. Campus accommodation is a categorical attribute. But there's more. Another example here could be motivation for why the student enrolled into the program itself. Now, in that particular case, the input variable is not categorical, it's not numeric, but rather it's text, is it? And because it's text or content, what you would need to do is to view it from the perspective of one of those outputs after you transform the text, is it? If you use count vectorizer here, you have like a vector representation, yeah? A vector that comprises of words or phrases, I want to say, in an event where you're using bigrams or trigrams or something. So in essence, if you're working with text, your input features are not as simple as course workload, Moodle weights, or campus accommodation. In fact, it gets even better. If you're working with nominal attributes, like because campus accommodation is dichotomous, is it? Yes, no, it's binary, right? 1 or 0. But if you're working with something like course minors, where you have a series of minors, what we're saying is that your input variables or your features would not really be that single, guys. Your input features would not be, yeah. I'm just going to import pandas as PD. And then I'm going to say student database is equal to pd.read CSV. Just see if we can speak to the dataset itself. What we're saying is that for a variable like this, because we have, and I'm going to cast this here to a set and then cast it back to a list or something so that it's a lot easier. Because we have a number of minors, right? We have physical education and sports, one, French, geography, civic education, religious education, mathematics, art and design, English and history. There's 9 of them. So in essence, if we're using this as an input feature, what we'll do is our X would comprise of one hot encoded version of this, is it? So in essence, what you would do is you would say pd.getDummies. Right? So you'd have this as your input. Is making sense, yeah? And then when you're working with text, you know the drill, right? When you're working with text, what you are doing is you're saying you're going to get the text itself. You do the usual preprocessing, and then you're going to get the text itself. But what you're doing with your text is you're going to have to vectorize, right? You're working with your corpus, your entire corpus. You identify the vocabulary in your corpus, and the words in your vocabulary, when strung together, will form a vector which collectively will comprise of your input features, your X's. Now, the key thing here is that the feature, uppercase X, is uppercase X because it's a set, right? It's a set of different attributes. Could be one, could be multiple. Anyways, and then the target will also be referred to, or is also referred to as a label. It's represented by y, lowercase y. And really, this is nothing more than the output variable that you want to predict. In our example, for supervised machine learning, what we're interested in predicting is whether the outcome is a pass or a fail, okay? In other instances, you may be interested in predicting whether the outcome is like a type of government gazette, or it could be a type of publication so that you classify it or something like that. And then what we're calling an estimator or a model, I know some of these things are interchanged somehow, but we're calling an estimator or a model as an object that learns relationships between the features, uppercase X, and the target Y. Okay? So in essence, really, it's the output of the training process. It's what we're calling a model and estimator. Now, I'm going to use this interchangeably because when you're saying model, what we're saying is that it's a thing that you are learning, is it? The thing that you're training. But the word estimator, I use the word estimator to refer to a specific algorithm that you're using to implement the model, to learn the model itself. So is it naive Bayes? You know, is it decision tree classifier, for instance? stochastic gradient or SGD classifier or something like that, right? Or naive Bayes, right? So an example of an estimator within the context of our terminology here would be a decision tree classifier, right? Object. And then whenever we're making reference to training, we are referring to the process of fitting the model, learning the model, right, on the training data itself. And the correct term actually is fit. In fact, the methods that you use to learn the model is a fit, right? So it's a dot fit. On the object itself, so on the decision tree classifier object, you run the fit method to train the model so that it learns, right? And when you fit it, what you're doing is you're saying you're learning the model will learn the pattern during the fitting process phase itself. And then prediction, also called inference, refers to using the thing that you've learned, the model, right, that you've learned here to make a prediction on new unseen data. So typically, at a bare minimum, this will be on data that forms your test data set. In fact, this is why sometimes, depending on sort of text that you're reading, they refer to this process as inference. Is it you're running inference on a model, right? You're predicting, but inference sounds more appropriate, fitting here. Anyways, now what you will notice here is when I start running you through the code, you will notice that the uppercase X here will typically be a 2D object, right? And in fact, you notice when we're splitting the data that we'll be using double square brackets for extracting the X's, whereas for the Y, it will be like a single square brackets, right? Which is a series. It's a subtle difference, but when you're getting started, you may probably run into errors and you'll be wondering why this is the case, right? Just remember that the APIs we're going to be using from scikit-learn require that X, which is a set of features, or the features must be 2D objects. So anything that is a 2D object can be fed, right? Or can be represented by this variable uppercase S. Yeah, so X must be a 2D object like a data frame, and then the model must be able to handle one or many feature columns, right? So in as much as the very first examples I'm going to showcase to you, we'll use a single input feature. So uppercase X will just refer to a single feature. But what we're saying is that you can actually learn a model in such a way that you are feeding it multiple X's, right? In fact, it could be the entire set. You can feed it all of these variables at once. If you're trying to learn a model that takes in workload, model hits, and campus accommodation all at once, right? All you're doing is you're making sure that you're feeding these variables as a 2D object, right? Anyhow, so you'd use the double square brackets, right? And the idea here is this keeps the input structure consistent, so it's 2D here. It doesn't matter whether you are working with one feature or thousands of features. Be consistent like that. And the shape will just be the number of samples, number of features. So whenever you see me running shape, it's like the same function we were using when we were working with those sparse metrics. Okay. And then the Y, which is the target, must be a 1D object, one-dimensional object. For instance, the easiest one-dimensional object that we've already introduced you to is a series, but it can be any other object, right? Typically, it works best here if you just, when you're actually learning the model, just make sure that you're working with a data frame, or a data frame for your uppercase S and your series for your lowercase y. It'll be a lot easier that way. But just to let you know that you can feed these APIs we're going to be using with other data structures as long as they're 2D and 1D respectively, right? For uppercase X and lowercase y. Again, just put things into perspective here. We see that for your X's, uppercase X, the syntax is such that we use double square brackets, whereas for lowercase y, it's single square brackets, right? The data type typically would be something like a pandas data frame for your uppercase X and the pandas series for lowercase y. The dimension obviously is this 2D object for uppercase y, 1D object for lowercase y. And the purpose here is obvious for uppercase y is to hold one or more features, whereas for lowercase y here is to hold the target itself. Okay. Now, it turns out that when you're using scikit-learn is implemented in such a way that it uses a consistent API. You should probably find time, ladies and gentlemen, to look at the history behind scikit-learn, right? It started off not just as a single, machine learning library here. Has a very interesting background here. You probably want to look into that. But what we see here is that most of the estimators or algorithms in the scikit-learn library will use a simple yet consistent pattern. So irrespective of whether using decision tree, SGD, naive Bayes, support vector classifiers, what we'll be doing is we will have to import the model class from the library. For instance, if you are wanting to use decision tree classifier, what you do is you'd import it from sklearn.3, okay? And then you create an instance of that model class. Yep. Typically, depending on the type of model class that you're using, it's possible that it may require that you feed it optional parameters. Like in the case of the decision tree classifier, there's a random state parameter that you feed it, right? In some instances, you can get away with not feeding it any hyperparameter at all. Okay, so instantiate an instance of the model class, and you set in parameters where applicable. And then step number 3 is you have got to fit the model. So you are learning it or you're training it on the training data. Now you notice here, you import, you instantiate. At the point when you're fitting the model, you're learning the model. The assumption is that you are using the training data set. Remember we mentioned that in step number, I'm going to go back here. In step number 3, we are splitting our labeled data set into 2, right? Into separate sets for training and testing. The fitting makes use of the training data set. Yeah. So step number 3, you fit or you learn the model. What you're doing is you're training the model on the training data set or on the training data. This is in essence a learning step. And the fit method is the thing here, always takes the training features and training labels as input. And this makes sense, right? If we are saying that the fit process helps you learn the model, then for you to learn the model, you need 2 things, is it? The target and the input. If we need the target and the input, or if we need the input, which is uppercase X, and the target, which is lowercase y, then what this means is that the input is actually from the training set. So by convention, putatively here, we're going to be referring to the training data set with the word train, right? Uppercase X _ train means we are picking input features from the training data set. And the lowercase y _ train means that we are picking corresponding targets or labels from the training data set. And then we fit. So you notice from the example here, right, in red, using the instance of the model we created in this particular case using decision tree classifier, what we do is we run the fit method by feeding it 2 parameters. First parameter is the features. The second parameter is the labels. So we're telling it, here are the inputs and here are the corresponding labels from our training data set. Okay, and then step number 4, once you learn the model, is you do your predictions. So you notice here the predictions are being done on the test data set, yeah? var _ uppercase X _ test. The idea here is, in as much as we can actually do a var _ model.predict var _ X _ train, it wouldn't make sense because we'll probably get an accuracy that is equal to 100%. Why? Because we'd be testing the model on the things it has been trained on. It's like us right now, right? We tell you that you're writing a test on Thursday, and we tell you to say, here are the questions that are going to come in the test. Obviously, you're going to get everything right, unless if you're lazy like that. What we'd much rather do is we tell you, here are some practice questions, and then when the test comes on Thursday, we are giving you completely new questions, right, that you haven't seen before. That's a more objective way of testing. So again, prediction is done on the test data set. Hope this makes sense. So it turns out that it's the same, right? Whether using decision tree classifier, naive Bayes, stochastic gradient descent, support vector classifier, it's all the same. Now, we sit here and it becomes important for us to discuss an important question of how then do I choose the correct estimator to use? If Lighton is saying, if Lighton is telling you that when you go to, and this doesn't necessarily have to be sklearn here, I'm just going to use sklearn here. From sklearn, I'm going to say import sklearn or something like that. It's a lot easier here, but I'm going to say from sklearn, I don't know why it's taking long here, but from sklearn dot tree dot. If we're saying, if we're saying that there's a whole range of there's a whole range of estimators that you can use, the obvious question to ask is, well, how do I know the appropriate type of estimator? By the way, for decision trees, you get them from sklearn.tree, but what you'll notice is that there's a whole range of if I can go somewhere up here and try and see which other things I'm using here. Decision tree. Okay, maybe naive Bayes or something. So sklearn naive Bayes, right? What you notice is there's a whole range of estimators that you can use. In fact, if you use the scikit-learn map, which I've introduced to you in previous sessions, this diagram here, you notice that you have quite a number of options here. And the question is, well, I mean, how do I know what to use, right? What do I use here? Now, in an ideal case, we're supposed to have like probably a mild introduction to the theory behind some of these popular estimators, but this is the last week of classes. I decided to just dumb it down a little and just highlight the fact that you can use this map ideally, right? As a starting point. It's a good enough starting point. So scikit-learn, library documentation provides a cheat sheet guide, right? This diagram here, which you can use, right, to make a decision on what sort of estimator you can use. So you can ask yourself questions like, are you going to be predicting a category, right? The thing you're predicting, is it a categorical attribute or is it a numeric attribute, for instance? Right? If it's a categorical attribute you're predicting, you know that you're solving a classification task. Yeah. If that is the case, you ask your question, do you have text data? Is your uppercase X, does it comprise text data? If it does, if uppercase X comprises of text data, you first of all start off with naive Bayes, for instance. Otherwise, you can start off with logistic regression, k nearest neighbors, support vector, classifier or support vector machines or something. But it turns out that decision trees are also a great choice, right? Sweet spot here. You can use them in multiple instances. You probably want to look at this diagram here. Or you can ask yourself a question, if you're not predicting a category, are you predicting a quantity? Is it a number, continuous attribute, right? Let's say test scores or incomes. So you can start with linear regression or region, right? Or are you looking for groups, right? So you're not predicting anything, but you're looking for patterns. Do you know how many groups, right? So you say, well, you're going to use k-means clustering, for instance. Do you want to find clusters based on density and identify any sort of outliers? You use dbScan, right? Or are you trying to visualize or reduce the dimensions? So you have X comprising of thousands, right, of attributes. And because it becomes difficult for you to visualize thousands of attributes, what you can do is you can reduce the dimension of your vector and use principal component analysis, for instance, or PCA, right? Again, this is a really nice starting point. So in your respective groups, when you're thinking of modeling here, which is due Friday, you start here, right? You say, do you have more than 50 samples? Yes. Are you predicting a category? If it's yes, then you go to the left, right? Yeah. If you're not predicting a category, if you're predicting a quantity, you go to the right. And then you're playing around with either what's on top here or at the bottom. Do you understand? So you see here that there's a whole range of options here, is it? SGD, classifiers, kernel approximation, k-nearest neighbors, support vector classifier, SVC, ensemble classifiers, naive Bayes, linear, support vector classifiers, a whole range of things here. Okay, so what we're saying here is there's a systematic method you can use to choose the correct estimator. I think this is I want to call this a lazy man's approach. But ideally, as good computer scientists, what we must do is we must read, right? We must familiarize ourselves with the theory behind all of these different estimators. In fact, in addition, as good scientists, in the School of Natural Sciences, we must do what? We must experiment, right? So you can have a series of options, maybe 10 estimators that you can potentially use. What you can do is you can experimentally determine which one would be appropriate by choosing the thing that's going to yield the best result in terms of a metric like accuracy or precision or recall, depending on the sort of task that you're solving. Okay? Anyways, so there's that. Now, just to mention here that in the case of the examples in this lecture series, we are predicting a category, right? Pass or fail, right? So what we are solving here is, if you go back here, what we are looking at is what's on the left here. In fact, we start, we check, is the sample is greater than 50 years? Are we predicting a category? Yes. Do you have labeled data? Yes. So we are here, right? These are the options we have. So since we'll be working with text data, right, we could, this. Since we'll be working with text data as input in one of the examples, we could use naive Bayes, for instance. Yeah. Text data, naive Bayes. For other data types, however, like I think one of the models, simple models that takes in a single X, uppercase X, uses campus accommodation, right? That's a binary. It's yes, no, is it? Dichotomous attribute. We can use logistic regression or decision trees, right? They're excellent choices for that sort of data type. Anyway, so just to mention here, this is the reason why we'll be using, these specific estimators for the examples. For clustering, main question to ask is whether you know the number of groups that you're looking for, which obviously will lead you down to use k-means clustering or something. I hope this is making sense here. I thought I would also sneak in something here as we are discussing the importance of splitting data here. Sneaking importance of splitting the data, is it? We are trying to avoid the problem of overfitting. We can, if we want, we can skip step number, I want to come back here. We can skip step number 2 if we wanted to. I want to say, we're just going to get our labeled data set and learn our mode on the entire labeled data set, right? In the case of students at risk of failing data set, it's like all the 273 observations are going to be used for training. But we will find ourselves experiencing a problem of overfitting, right? And overfitting occurs when a model learns the training data too well, so that it becomes so perfect, right? In essence, what it's doing behind the scenes is just memorizing the noise, right? In specific details of the training data. The problem with that is it fails to generalize. So if you give it new things, if you test it on the data you have, it will probably perform so well, right? It's in the 90s or maybe close to 99% or something like that. But if you feed it new observations, things that it hasn't seen, it fails to generalize, right? As a result, it performs poorly on unseen data, new and unseen data. I tried to use an example here. An example would be you're memorizing the answers. I've seen you in the quiz, right? You suspect we're going to use the same data set. You memorize things, and there were people that were literally in the previous quiz, quiz 4. They were referring to the students at risk of failing data set. But that data set was from Zambian Watchdog, right? Facebook I mentioned. Why? Because you were memorizing the answers, right? Or you're memorizing the data set in essence. You failed, right? Because we gave you something that is completely new like that. Anyway, hopefully this example kind of resonates with what we're talking about here. Now, the symptom of overfitting is that you have a situation where you have high accuracy on the training data, but low accuracy on the training data, right? The opposite problem is called underfitting, which typically occur when a model is too simple, right? It's so simple that it's too simple to capture the underlying patterns of the data. So in other words, it fails to model the training data well. In fact, it also fails to generalize on new data. So what typically happens here is the model will end up making very strong simplistic assumptions about the data in essence. Again, I tried to include another example here. Hopefully it makes sense here. An example would be a student who reads like a summary, right? Before a chapter summary before the example. You have a general idea, but you can't answer specific and complex questions. A symptom, if you notice here, high accuracy, but the symptom here is low accuracy, right? So a model that suffers from underfitting has low accuracy, whereas a model that suffers from overfitting has high accuracy. Yeah. Again, just showcasing a video representation here of what would typically happen, right, when you're looking at overfitting and underfitting. I just have just a few notes explaining this graph here. We've already explained most of these things here. I want us to maybe briefly chat about how we go about splitting, is it? Because we've said that as part of step number 2, we must split the data. These slides are just explaining the graph. I'll ask you to just go through this here. I'm just explaining. I'm explaining the linear plot there. Now, the question to ask here is, how then do we split the data into training and testing, or into training, testing, and validation? Well, there are a couple of strategies. We're going to look at 2 strategies in 4792. We're going to look at one of the most popular strategies called the holdout method, where you just split your data set into a training and test data set. And then we'll discuss so-called cross-validation, or K-fold cross-validation to be specific, which is a more aggressive way of splitting your data set into training and testing. Yeah. So with the holdout method, what you do is you're partitioning or you're splitting the data into 2 independent sets: the training data set, which is used for training the model or for learning the model, and the test data set, which you use for evaluation, performance evaluation. The important question to ask is, if you have a data set like this, which has 273 observations, the question is, how then do we decide the number of things that we are going to put in the training data set and the number of things we're going to put in the test data set? Well, it turns out that the recommendation is usually that you have a lot more data in your training data set. In terms of specific ratios, there are certain recommended ratios that you find in literature. These are things that have arisen as a result of people, conducting a series of experiments. So 7:30 ratios are quite common, where 70% of the data is going to be reserved for training, and the remaining 30% is going to be reserved for testing. So in other words, in this particular example, what we are saying is that we are going to say 70%, which is about 192 data points are going to be used for training, and about, I'll say maybe 80 or something, well, 81, I guess, would be used for testing in this particular case. And these are done at random, right? Or in the case where you are using an 80-20 split, you would get 80% of the data for training and 20% for testing. Typically, these ratios would be used by taking into account important things such as the size of the data set. I'll be the first one to tell you to say, I don't think it would be wise for us to do a 70-30 split here, because 92 observations for training may not really be sufficient like that. you know, especially that we have certain variables that would need to stratify, right? Is it like gender, for instance, and all those things? So this may not really be wise. Anyway, so 70-30 split or 80-20 split is a good standard. These are good standards. They provide enough data for training and leaving a reasonable test data set. The idea here is when you're testing, right, you don't really need a lot of data for testing, but you need significant amount of data for training, which is why the ratio is usually skewed more towards the training data set. So you typically would have a lot more data in your training data set than in your test data set. You can also use a 90-10 split, where you have, in instances where you have a very large data set. Yeah, the problem with using in 90-10 split here is we would only have 27 data to be used for testing, which I guess would be okay, but not really okay. Anyways, so the question then is, how do we do this programmatically? I mean, it's not like you would want to, when you have a labeled data set with 273 observations, you just can't say, I'm going to get the first 191 attributes and then put them in my training data set and then get the remaining 81, or is it 82 attributes and put them in my test data set. You don't do it like that, right? You've got to shuffle these things in some instances. In other instances, you want them to be stratified. Is it because there's some data sets that will have certain variables that you'd want to be present in both the training and the test data set? Things like gender, things like minor description. You want there to be mathematics in the training data set and also mathematics in the test data set, right? It turns out that scikit-learn has an easier way, right? We can use the scikit-learn API to essentially split our data set into a training and test data set using the holdout method. What I'm showcasing here is a code construct that allows us to import train underbar test underbar split, right? That's a function that we use to split our data set from sklearn.model underbar selection. Okay. So the first step is you import train underbar test underbar split. This is a function that you use for splitting. And then after you do that, you run that function in essence to split your data set. Now, you may not really see this, so I'm going to run this from here. I'm just going to sklearn.model selection import train test split. You probably want to find time and read the documentation here to try and get a sense of the parameters, right, of this function. You notice it takes in an array, right, and then there are keyworded parameters. This is an array of your data sets, is it? Your uppercase X and your lowercase y in essence. So your data set, rather, not uppercase, your data set, and then you need to split it into your uppercase X and lowercase y. Two types of uppercase X and two types of uppercase of lowercase y's. These keyworded parameters allow you to indicate the proportion, right? Because you're using this for the holdout method. You can use the test size variable to indicate, to say, I want 0.3. This is a value between 0 and 1. I want this number of elements to be reserved for my test data set. The remaining will be the training data set. So in essence, actually, you fill out either one of these two. Typically, just say you indicate the test size or the train size if you want. So what we have here is a classic example. If you notice, pay particular attention to the last bit here, right? Where we are saying that we are going to split var x and var y. Now here's the thing. I'm going to just. Good evening, Joshua. Yes, I don't know what that is about here. I don't know what that is about. I don't know if there's a question. Please go ahead. Okay. Here's the thing. If you notice, right, the train split here, there's a couple of things here. For starters, forget the variables that I'm assigning here, because the way this works, you are splitting this thing into two, but you're splitting it into two in such a way that you have two pairs of uppercase X's and two pairs of lowercase Y's, right? This is what is returned here. So in other words, we are saying we are assigning these variables, this thing, to hold all the input features that are going to go into our training data set, hold all the input features that are going to go into our test data set, hold all the targets or labels in our training data sets, the Ys, hold all the labels or the targets in our test data set. But forget about this part here, right? Pay particular attention to the method. You notice that we are feeding this. In fact, forget about random state 42 here. What's important is these things here. What train test split takes in at a bare minimum is you must, well, actually, at a bare minimum is this, right? Because this is a key-weighted parameter. If you notice, split with the variable test size is going to be none, right? And guess what, right? If none, then it will be set to 0.25. Do you understand? So you don't have to worry about this. So it's like 0.25, 0.3. In other words, you'll be dealing with a 65 to 25, no, 75 to 25 ratio, if you don't specify 0.3. But at a bare minimum, we're saying you have to feed it this. Now, if you're feeding it this, right? And imagine a situation where your input X is what? I'm going to use campus accommodation. In other words, what you're saying is that for this thing to work, you have got to feed it. There's a couple of things here. var X is a 2D array. If you remember, var Y is a 1D array, is it? Yeah. I don't know if people are following through with what we're doing here. And the other thing to remember, and this is crucial, right? We are assuming at this point that we've already one-hot encoded these things. In this particular case, we have got to one-hot encode this because it's a categorical attribute, right? Yes, no, yes, no. So in other words, what we'll be saying is that using this for campus accommodation, would be doing this. Our X would be this. In fact, it wouldn't be this per se. Our X would have to be, you know what I'm going to do? I'm going to say, I'm going to say this. It will have to be this. Or something. Or you can still, it's fine. You can still assume that it's still var X is still this normal campus accommodation like this, and then later on you can do the modification. So in essence, we are saying var X is going to be this, and then our var Y, lowercase y, this is operative, is going to be what? Var Y is supposed to be this. Final examination. And I'm just going to say dot fill na 0, right? So in essence, it's supposed to be this, but this is not this is not yet converted into into true or false. We would have had to convert this already, is it? Somehow. Do something like this. 1010 something, right? Yes, no, something like that. And then you have this. I'll call this exam status, so that our var lowercase y is equal to this, is it? Right? So we have var uppercase y, lowercase y, and var uppercase x. And so what we're then doing is we're saying for us to split this, at the bare minimum, we use trend test split, and we feed it var uppercase x and var lowercase y, like this. Now, here's the thing. If I run it just like this, right? If I run it just like this, and I check the type, what you notice is that it's going to be a what? A list. And guess what? It's a list that comprises of 4 items. I hope it's a multi-dimensional list that comprises of 4 items. And those 4 items are created in such a way that, observe, the very first item, this has 4 items. The list has four elements. The first element at index 0 is this, right? Its input, it's uppercase X. Now, the trick here is the way you know which uppercase X this is you can check the length. 204. It's like 204 divided by 273 is 75%. So by default, we're using a 75%, 25% split, meaning that this element at index 0 is what? It's equal to var uppercase X underbar train. Do you understand? And then if I check the length of the second element, which is at index 1, it has 69. It has 69, and in fact, what I can also do is I can check what is in this thing here. It's still campus accommodation. Now, 69 divided by 273 gives you 25%. So what this is telling me is that the second element, this, is actually equal to var uppercase X underbar test, right? The third element at index 2, you guessed it, it has those exam scores, right? Pass, fail, 1 0, 1 0, 1 0, 1 0. If we check the length, and if you're following through, the length of this will be the same length as the thing that is at index 0, 204. So in other words, what this is it's var underbar small y underbar train. If we check the last element, which is at index 3, right? Because there are 4 elements in this list. You guessed it, it will be 1 0, 1 0, 1 0. If we check the length of this, it matches the length of the element, the list element at index 1, which is 69. And so what is this? Well, this is var underbar y underbar test. Do you understand? The holdout method. And indeed, because of this is the reason why the code snippet I had before had this. I'm going to undo this. I'm telling Python to say assign the variable var underscore x train to equal the first element in this list, resulting list here. This is going to be the second element. This is going to be the third element. This is going to be the fourth element. You understand? I'm just doing it all at once. If I wanted to, I could just as well have said this. If I wanted to, this is just a smart way of doing things here, right? I've just said this is equal to 0, right? This other one is equal to 1. This X test, if that makes sense. And then this is equal to index at 2, the var lowercase y train. Yeah. And then this is equal to index at 3 test, like this. So this is a more simplified manner of doing this. Now here's another thing, right? The test size, if you notice, if I change here, when I was creating trend test here, when I fed it these variables, right? Trend test here, if you notice this, sorry, when I came here and said I want to run trend test like this, you see, what I did is I'm using default parameters, is it? These default parameters here, where test size is none, trend size is none, shuffle is true, stratify is none. Now you can get away with all of these defaults. It's fine, nobody cares, right? But at the bare minimum, if you require to use a 70% split, what does that mean? It means that you're saying that your size, right? You can think of the range 0 to 1 here as being a scaled version of 0 to 100 or something. So if I come here and I say, look at this, I come here and I say test size is equal to 0.3, and I check what is the size of this element here. You see this? What I'm saying is that I want the test data set to comprise of 30% of my labeled data, 0.3 times 100, right? If I want to use the 80% split, I would say, and true to that, if you check 191 divided by 273 times 100, is going to give you 70%, 69.96 is 70%. If you want to use a 80-20 split, you'd say, I want you to use the test data set comprise 0.2 times 100 is like 20% of the data. And true to that, if I check the length here, 218. If you notice, is this making sense? Don't know if it's making sense here, but anyhow, quite a number of things here happening. I hope this is making sense to you guys here. Anyways, so we are saying here you use what we're saying, most data splitting strategies is the most common method of splitting data is using the holdout method. You're holding out the test, is it? It's also so the holdout method, the trend test split function from scikit-learn makes it easy for us to do this, and your choice really can be based on what's available in literature, right? These are putative ratios, which work surprisingly well. So for most problems, if you use these ratios like 80-20, 70-30, 90-10, you do just fine, right? Now, when we meet on Thursday, I'm going to show you guys how we use the K-fold cross-validation. And then we immediately transition to start looking at model implementation. I'm going to pause here and ask if there are any questions about this. Yeah, I don't know. Awesome. Okay, if there are no questions, thank you very much. Then we shall. Somebody here says, I wanted to ask about our data set for training the model. In our UNZA journals, we only have. Yeah, but I answered. Talk to your colleagues. I think I answered this question. Your colleagues literally asked this question the other day, and I don't know about the 47 articles here. Just train it. Build a model that's based on the data that you have available. It's okay. It's okay even if you get 30% accuracy or something like that. Doesn't matter. I'll be in the office tomorrow if you want to see me, Kasweka, Michael. I'm going to be in the office tomorrow from. I have a series of meetings, so I'll be in the office from 8. But I have classes mid-morning. I have meetings in the afternoon. So if you want to come and see me, you will find me in the office anytime between 8 and 10:45. You will find me. Okay, come through. Thank you very much, everybody, and I will see you. Please prepare for the test on Thursday. It's day after tomorrow. Bye.
Ah,